Hi everyone, welcome to our video lesson on factoring dots. Go ahead and grab your notebook, find the next available page, and title the top so that you can take notes along with this video. Now, before I go into what dots stands for and what dots is, I want to actually backtrack a little bit and go over some problems on multiplication that we saw in our last unit. So I'm going to write two questions down. Feel free to pause the video and try them on your own before I put up the answers. But more importantly, look at the similarities between the two questions, both where we start and what the answers are as well. Okay, so a little review. First one is x plus 3 times x minus 3. And then the second question is a minus 5 times a plus 5. So if I come over here to the first example, and we're going to double distribute, x times x gives me x squared, x times negative 3 gives you negative 3x, 3 times x gives me positive 3x, and 3 times negative 3 is negative 9. Always combine like terms and put your answer in standard form. So negative 3 and positive 3 are like terms that actually add to 0. So my final answer is x squared minus 9. Over here, a times a is a squared. A times positive 5 is positive 5a. Negative 5 times a is negative 5a, and negative 5 times positive 5 is negative 25. Again, we have like terms in the middle here. Both positive 5a and negative 5a have a to the first power, but they cancel out to 0, so I'm left with a squared minus 25. Did you catch the similarities in those two questions? Okay, both of our factors that we started with had very similar terms in each factor. This is a binomial with x and 3, and this is a binomial with x and negative 3. Similar over here, this one is a binomial with a minus 5 and a binomial with a plus 5. So we've got two terms in each of our factors, very similar terms as you compare the two factors together, but one has a subtraction sign and one has addition. Okay. Both of these multiplication questions led us to binomials with subtraction in between the two terms. And if you investigate each of those individual terms, you have perfect squares. 25 is a perfect square, 9 is a perfect square, and both x squared and a squared are considered perfect squares. Okay, those are dots. So when I am looking to recognize dots, and this is where we'll get into what dot stands for, I'm looking for the difference of two squares. And some people like to throw perfect squares in there, but it throws off our whole acronym if we have a P in between there. So we're looking for the difference of two squares, and you'll see that here we have subtraction in between a squared and 25, and over here we have subtraction in between x squared and 9. And the great thing about this is if we recognize that we have the difference of two squares in our factoring questions, then breaking it down back into the two pieces that would multiply together is very simple. And it always fits the same pattern, and you guys will get the hang of that in no time. Okay, so very important before we dive into the actual factoring is perfect squares, right? We should all know our perfect squares numerically based on what we learned in middle school and based on what we worked on in the last unit. But if you need a reminder off to the side, let's make a list. Okay, our perfect squares, and I'm going to leave some space because we're going to add to this list. Our perfect squares are numbers like 1, 4, 9, 16, 25, and so on. Okay, and all of these numbers are considered perfect squares because if I take two identical factors and multiply them together, I get one of these results. 5 times 5 is 25, 8 times 8 is 64, and so on. So the question becomes, how do we know if we have perfect squares with variables? Well, a times a gave us a squared, so I know a squared is a perfect square. But what if it's not a squared or x squared? What if that exponent is different? And I'm going to write a list of some perfect squares using the variable x and see if you can catch on to the pattern of what makes a variable a perfect square. So we know x squared is a perfect square, but we also can use x to the fourth, x to the sixth, x to the eighth, and just like our list of numbers over here, there are obviously more options for perfect squares with variables. And I use the letter x because it's the most common, but obviously these can be y's or a's or b's, whatever it is that they're using. So what is the criteria or what is the pattern that we need to see in order to have a perfect square with a variable? Okay, well, you'll notice the important part or the changing here is in our exponent. And the only requirement is that our exponent is even. Okay, this stems from the fact that when you multiply variables with the same base, we actually add their exponents together. So we saw in our question that x times x gave us x squared. Well, if we take two identical variables and multiply them together, like x squared times x squared, we're going to get an even exponent in our result because we're adding these two together. So I can keep going. X to the third times x to the third is x to the sixth, and x to the fourth times x to the fourth is x to the eighth. And you're hopefully catching on at this point. So as long as I have an even exponent on my variable, I have a perfect square. And finding the square root of that variable is actually as easy as cutting this number in half. The square root of x to the eighth is x to the fourth, because x to the fourth times x to the fourth is x to the eighth. The square root of x to the 20th is x to the 10th. And all I have to do is cut that exponent in half. And we'll see that in a couple of examples. So with that in mind, with our new concept of variable perfect squares, what I'm going to show you guys is how to actually factor things that are considered dots. Okay, so the algebraic definition of dots, or the kind of go-to pattern that we're going to look for, is anything squared minus something else squared. Okay, now they don't both have to be variables. A can be a number, B can be a number, and you probably won't see this exponent of 2, but this is just a notation to show that you're going to have a perfect square minus another perfect square. And if you look up here, these are the factors that got me to x squared minus 9. And these are the factors that got me to x squared minus 25. So if it's my job to go backwards, if I'm given a question like this and it's my job to tell the reader the factors, I have to take the square root of my first term. So x squared, the square root of x squared is x, and that shows up in both my factors. And then I take the square root of the second term, the square root of 9 is 3, the square root of 25 is 5. And as long as one factor has addition and one factor has subtraction, we're going to get that canceling out motion in the middle, and that's how we end up with our dots. So if I see dots, if it's my job to factor it, I know that anything in this format is equal to a plus b times a minus b. And this is something just generalized to keep in mind. This is the format that we're going to follow for every question that requires dots. So let's look at some actual concrete examples. Okay, number 1. If someone asks me to factor x squared minus 36, that's a polynomial, specifically a binomial. It has subtraction in the middle with two perfect squares, so it fits my criteria for dots. That means that if I want to break this down into two pieces that will multiply back to that binomial, all I have to do is take the square root of x squared, which is x, the square root of 36, which is 6, with one factor having addition, one factor having subtraction, and my job is done. This right here is the factored form of x squared minus 36. Let's try another one. How about y to the 10th minus 49? We've got the difference of two perfect squares, so I know right away that it's going to fit my format up here. The square root of y to the 10th, remember to cut this exponent in half, is y to the 5th, and the square root of 49 is 7. As long as one of your factors is subtraction and one of your factors is addition, it doesn't matter which one is which, you're done. And those are your factors. Now for the next two, I highly encourage you to pause the video, try them on your own, see if you're getting the hang of this already, but we will go through them together. So number 3 is going to be 100 minus x to the 4th power. And number 4 is going to be 16a squared minus 81b to the, let's go with 6th. So for this one over here, the important thing is the order does matter, right? Subtraction's not commutative, and when it comes to factoring, we want to make sure that we end with this polynomial if we were going to multiply our two factors together. So when I notice that I have dots and I set up my two factors, I'm going to take the square root of the first term. Square root of 100 is 10, and that square root comes first because my 100 was first in my original polynomial. The square root of x to the 4th is x squared. When I cut that exponent in half, I get 2. And as long as one of them is addition and one of them is subtraction, you did it correctly. Okay, last but not least, if I'm trying to take the square root of a monomial that has both a coefficient and a variable, I'm going to take the square root of 16 and then take the square root of a squared, but keep them together as one term. So the square root of 16 is 4, and the square root of a squared is a. So together, the square root of 16a squared is 4a. The square root of 81 is 9, and the square root of b to the 6th is b to the 3rd. So my second term is 9b to the 3rd power. And again, as long as one factor is addition and one factor is subtraction, you've done it correctly. Now keep in mind that any of these 4 answers can be checked if you have spare minute by double distributing just like we did up here. If you multiply these together and you get back to x squared minus 36, you did it right. If you didn't, then go back and double check, make sure you took your perfect squares correctly, your square roots I should say correctly, and make sure that you have one addition and one subtraction in your factor. That's it for today, so bring any questions that you have into class tomorrow, and I'll see you then. Have a great day, guys.